Welcome to S1 Lesson 6, Discrete Random Variables. Before we start, if you can make sure that you've got a copy of the presentation slides printed out, because you may want to make some additional notes and it'll make perhaps attempting the questions a little bit easier to follow. Also, if you make sure that you've got pen, paper and calculator, as I just mentioned, you are going to be expected to perhaps have a go at some of these things yourself in this video. So just a recap of where we are, we've now completed the probability module of S1, and what we're looking at and we're starting today is the discrete random variables module. So, discrete random variables. A random variable, first of all, is the set of outcomes for an experiment or an event. It's as simple as that. So heads, tails, these are random variables. Rolling a dice, 1, 2, 3, 4, 5, 6, these are random variables. Any outcome of an experiment or an event is a random variable. A discrete random variable is a variable where the outcomes can be listed. So flipping a coin, discrete random variable, heads or tails. Rolling a dice, discrete random variable, 1, 2, 3, 4, 5, 6. Okay. Now in general, discrete data is something we consider as something that can be counted. Now I mentioned flipping a coin, it's heads and tails. Perhaps what we'd do in that case is count the number of heads or count the number of tails. Okay, so it's a new topic. What we need to look at is a couple of bits of notation. We tend to signify or denote a discrete random variable by using an uppercase letter such as X, Y or Z, and then we can represent the particular values that a discrete random variable can take with lowercase letters, and we'll clarify this in a moment. Subscript is often then used to represent multiple observations of the same random variable, so we may look at a random variable X and look at the experiment or event a couple of times. Now just to clarify this, what we mean then is, so if I've got this statement here, this reads as probability of the discrete random variable X is equal to the specific value, whatever X may be, equals 1/4. And so here's some various ways that we can write this down here as well. So here looking at a particular observation value, or just writing probability of X. Now probability distributions. If a discrete random variable X can take possible values x1, x2, x all the way up to xn, with probabilities p1 for x1, p2 for x2, so on, so we've got pn for xn respectively, then if we add up all of these probabilities, that's equal to 1. And that is what a probability distribution is. Okay, so a probability distribution for rolling a six-sided dice would simply be probability of 1 equals a sixth, probability of 2 equals a sixth, 3 equals a sixth, 4 equals a sixth, 5 equals a 6, 6 equals a 6. And obviously that's quite a lot of information, so what we do is tabulate this. So let's have a look at an example where we can actually have a look at this. So we've got 2 coins are flipped and the number of tails are counted. Write out the probability distribution. Okay, so we've got 2 coins are flipped. So then what we're going to say, X is the number of tails. So we're just identifying the value at the discrete random variable that we're using. So then what I can put in my table, X equals, and we're going to put probability X equals X. In fact, we should really use a small x up there to represent our specific values. So what values, how many tails can I have if I flip a coin twice? Well, first of all, I could get no tails. Second of all, I could get 1 tail. Third of all, I could get 2 tails. Now, there's a couple of ways we can go about finding the probabilities of these events. I think probably the simplest way with 2 coins where there's equal probabilities is just to list the outcome. So I've got a head and a head. I can have a head and a tail. I can have a tail and a head, or I can have a tail and a tail. So probability of no tails is going to be 1/4. Probability of 1 tail will be 2/4 or a half. Probability of 2 tails is 1/4. And this here, this represents the probability distribution of the discrete random variable x. Probability, let's make sure we spell this right, let's have no spelling errors in here. So probability distribution of x. Okay, so the probability distribution is just literally listing the outcomes and the probabilities associated with those outcomes. Okay, so let's have a look at one for you to try now. A bag contains 4 blue discs and 3 green discs. 2 discs are removed without replacement. The random variable x is the number of blue discs removed. Find the probability of x. Okay, so at this point what I want you to do is stop the video and I want you to try this out for yourself. Okay, so let's have a look at the answer to this. Okay, so we had, let's just note down a couple of things. We had 4 blue discs and 3 green discs. We want to count the number of blue discs removed when we take out 2 discs. So if I tabulate this, we can have the possible values of x. So first of all, we could have, so if we say somewhere on here, x is the distribution where it is the number of blue discs. Okay, so I could have 0 blue discs, I could have 1 blue disc, or I could have 2 blue discs. So let's calculate the probabilities of these happening. So probability of 2 greens, essentially, which is 0 discs. Well, that would be 2 greens. First of all, the first green would be a probability of 3 out of 7. And then the second green would be 2 out of 6, because there would only be 2 green discs left out of a total of 6. So we get 6 over 42, or 1/7. Probability of, let's say, 1 blue. Now that's going to be the probability of either a blue and a green plus the probability of a green and a blue. So when I work this out, this would be blue and a green. Well, probability of getting a blue first of all is 4 out of 7 times by, there's 3 greens left, so I'm going to multiply that by 3 out of the 6 counters that left. And then if I add, probability of picking a green first is 3 out of 7, and then probability of picking a blue second is 4 out of the 6 counters that are left. Now, when we work through this and do this on our calculator, we should get 24 over 42, which is 4/7. Okay, and finally, 2 blues. So 2 blues is just probability of a blue and a blue, which is then, okay, probability of getting the first blue is 4 over 7, multiplied by the probability of getting a second blue, which is 3 blues left out of a total of 6. So we get 12 out of 42, which is 2/7. So the probability distribution that you should have got was 1/7 for 0 blues, 4/7 for 1 blue, and 2/7 for 2 blues. Now I had to be careful on this one because it's slightly different to the one I did previously. I couldn't just list green green, blue green, green blue, and blue blue, because the probabilities of these things happening weren't equal. So I couldn't just say, okay, probability was a quarter, a half, and a quarter, because as you can see, the probabilities are not equal. Okay, I hope that made sense. So let's move on a little bit. So one thing that can be important, it doesn't come up too much in the WJC S1, but it's important to understand that our distributions can be represented by graphs. So here we can say that y takes the possible outcomes 0, 1, 2, 3, and that they have probabilities 1/12, 1/3, 1/6, and 5/12 respectively. So if we drew a diagram to illustrate this, we could use like a line graph like this, so you can see that these are the probabilities of each of those events, or we could use bar charts. So these would be discrete, so I would perhaps draw them something like this to represent those probabilities. Okay, so it's just a little note there about how we can graph probability distributions, and this will become more relevant later on with some of the other topics that we study. Okay, so we need to look at how do we use these probability distributions, and actually you've got the skills to, should have at this point the skills to use these distributions. We just want to demonstrate how the skills that you've got linked to this new content. So first thing to know is that each outcome in a probability distribution is mutually exclusive. So if we have a probability of one value or another value, then that is equal to the probability of the one value happening plus the probability of the other value happening. The other thing that we need to remember is the rule of total probability states that the sum of all the probabilities should be equal to 1. A little bit more content. Probability density functions. Okay, so probability density function, probabilities in a probability distribution can be defined by a probability density function. Now what this means is that we can have some sort of function which actually calculates the probability. You'll find that while a lot of probability examples that we use perhaps in GCSE have real life contexts, and like the last two examples we've done, we can calculate them from information we're given. Sometimes there's just probabilities of events that are not going to have any sort of context, and the way we calculate the probabilities of those events occurring will be using a function, or what we have called here the probability density function, and this is often abbreviated to p.d.f. Okay, so we're going to have a look at an example which incorporates these ideas. So we're given the probability distribution function. Now here's our probability distribution function. It's k over xn, and the different x values can be 1, 2, 3 or 4. So we've got three questions here. We want to write out the distribution in terms of k first of all. We want to find k, and we want to find the probability that x equals less than 4. So these are three typical exam style questions that we're going to encounter. So let's have a look. Let's remind ourselves that the probability density function, probability x equals x, was given as k over x. So what we get in the first one, k over 1 is just k. K over 2, x equals 3, we get k over 3. X equals 4, we get k over 4. Okay, and that's part A, just actually writing out the distribution in terms of k. Part B wants us to find k. Now the way we find k is that I know that the probability of summation of the probability of x must be equal to 1. So that means when I do k plus k over 2 plus k over 3 plus k over 4, this is equal to 1. Now, if I was to total up the left-hand side, essentially we've got 1 plus a half plus a third plus a quarter. So we can just kind of forget the fact that there's k there at the moment. We've got a third, so we've got 1 plus a half plus a third plus a quarter. This gives us 25 over 12, k, equal to 1. Now if I times by 12 and divide by 25, what I get is that k is equal to 12 over 25. And that's part B done. It just relies on total probability, so summing up these probabilities and getting a result of 1, and then solving that equation to find k. Part C wants to find a probability that x is less than 4. So this is the probability of x equals 1 plus the probability x equals 2 plus the probability x equals 3. Remember, all of these events are mutually exclusive, so I just total up their probabilities. I can do this in terms of k, so I'm just going to leave it as this for the time being, k plus k over 2 plus k over 3. Now what this gives is 11 over 6k, which of course means that I can do 11 over 6 times by 12 over 25. When I work through this, I get the probability that x is less than 4 is given as, well, I can cancel these, so I get 22 over 25. I may as well just leave that as a fraction. Okay, well I hope that made sense, because now here's one for you to try. Given the probability distribution function, probability of x equals xn equals k of x squared, where x can be equal to 1, 2, 3 or 4, write out the distribution in terms of k, first of all, for part A. Part B, find k, and in part C, find probability x is greater than 2. So if you pause the video at this point, and we will resume with an answer in a moment. Okay, so let's have a look at the answer to this problem. Let's just remind ourselves that we had the probability distribution function probability x equals x is given by kx squared. So getting a table in here, we knew that x could be 1, 2, 3 or 4, and so we say probability x equals x. So kx squared, k times 1 squared just gives me k. K times 2 squared gives you 4k. K times 3 squared gives you 9k. And k times 4 squared gives you 16k. So that is all that's required for part A, is to just write out that probability distribution in terms of k. Let's look at part B. Part B is going to find the probability, find k. So what I know is the summation of the probabilities of x should be equal to 1. So that means that k plus 4k plus 9k plus 16k must be equal to 1. When I total this up, I get 25, I get 30k, sorry, just skipping ahead of myself there, equals to 1. And so when I divide by 30, I get that k equals 1 over 30. Okay, so part C says, let's find a probability x is greater than 2. So how can I find the probability x is greater than 2? Well, it's got to be either probability x equals 3 or probability x equals 4. So I'm just going to total up these probabilities. So I get, and I'm just going to leave it as k at the moment, just as I did a moment ago. So I get answer of 25k. So in other words, I get 25 lots of 1 over 30. And you'll find that sometimes it just helps to have the k in there instead, because you don't have to deal with the fraction until right at the very end. So probability x is greater than 2, cancelling down the fraction, you get 5/6. Now hopefully you managed to answer that question and you've got the matching answer. So last part of theory now, independent observations. So if we have independent observations of a discrete random variable x1, or discrete random variable x, where we have x1 and x2. So here are my independent observations. Here's my first observation. Here's my second observation. If I want to calculate the probability of x1 being equal to one value and x2 being equal to another value, then because they are independent, what we know is from probability already, probability of A intercept B is the probability of A times the probability of B. So this is exactly the same rule that we've learned previously. We actually covered this in the last Teach Yourself S1 lesson, and this is just putting it in notation linked to discrete random variables. It means exactly the same thing. Okay, So let's have a look at an example and see how we'd apply this theory. A discrete random variable x has a distribution shown in this table. We're told that x1 and x2 are two independent observations of x, and so we want to find the probability that x1 is equal to x2 plus 1. Okay, so let's have a look at this. Here's my distribution. I'm trying to find a calculated probability that x1 is equal to x2 plus 1. So in other words, what's the probability that the first observation is one more than the second observation? So this is going to be the probability of x1 being equal to 1 and x2 equal to 0. Or probability x1 equals 2 with intersect x2 equals 1. Or, and I've run out of space there, so just resume it on the next lesson, we can have probability that x1 equals 3 and x2 equals 2. And these are all the ways that we can have the first observation, x1, one more than the second observation. So now I just need to calculate these. And notice, I kind of assumed here that from the properties of discrete random variables, these outcomes are all mutually exclusive because they're different. I can't have x1 equal to x1 as 1 and x2 equal to 0 at the same time as this second observation, and so on. So when I calculate this, I get probability of x1 equals 1 is 0.1. Because they're independent, multiply the probability of x2 equals 0, 0.1 times 0.2, plus. So x1 equals 2, 0.4, times x2 equals 1, 0.1, plus x1 equals 3, so 0.3, times x2 equals 2, so that's 0.4. And so when we work through this calculation, and it can be typed into your calculator all in one go, we should get the answer 0.18. And that is how we work with independent observations of discrete random variables. The trickiest part of the question, in all honesty, is this first part here, making sure that you list all the possible combinations of the independent events that satisfy the condition given in the question. Okay, well, I hope that made sense, because now it's time for you to try one. So let's have a look. A discrete random variable x has a distribution shown in the table. Given that x1 and x2 are two independent observations, find the probability that x1 plus x2 equals 4. Okay, now be careful with this one. Remember, we want to find all the different ways that x1 and x2 can combine to get this total of 4. So if you pause the video now, and we'll resume with the solution in a moment. Okay, so let's have a look at the solution. In this solution, we're trying to find a probability that x1 plus x2 equals 4. So let's just quickly, should have the table here really, but let's just quickly remind ourselves of what that distribution was. So we could have 1, 2, or 3, and the probabilities were 0.3, 0.2, and 0.5. So what are the ways probability x1 plus x2 can be equal to 4? Well, I can have probability x1 equals 1 and x2 equals 3, plus the mutually exclusive event x2 equal, sorry, it shouldn't be x2, it should be x1, the first observation first, obviously. x1 equals 1 and lack of concentration there. Let's think about this again. So we want to have x1 equal to 2 intersect x2 equal to 2. And then finally, probability that x1 could be equal to 3 intersect x2 equal to 1. Notice how when I've been doing this, I've been trying to be as logical and organised as possible. So with the previous example, I started with the smallest numbers and worked up. So here I started with x1 being the smallest possible number and then just worked through all the different x1 values that, one by one, and then obviously just paired x2 as the value which I'd totaled it up to 4. So now when I calculate this, we get probability of x1 equal to 1 is 0.3 times probability of x2 equal to 3, which is 0.5, plus probability of variables being equal to 2, which is 0.2 times 0.2, plus the probability x1 equals 3, which is 0.4, times probability x2 equals 1, which is 0.3. Okay, so when we work through this, you should find that you get an answer of 0.34. Okay, I hope that made sense and that you got a matching answer. So just to finish off this video, as it's quite a brief one, we'll look at an exam question, because one of the nice things about this topic is what we're doing already in the examples is very similar to what's asked in the exam. So let's have a look at this exam question. The probability distribution of a discrete random variable x is given by this probability density function. Okay, so here is our p.d.f. First of all, I want you to find the value of k and to tabulate the probability distribution. And second of all, if there are two successive values of x are generated independently, find the probability that two values are equal. So if you pause the video at this point, and then we'll resume in a moment with an answer. Okay, so let's have a look at the answer. First of all, let's tabulate the probability distribution. Now, coming across, I'm giving myself plenty of space on this one. You'll see why in a moment. We're going to have 2, 4, 6, and just extend it a little bit just so I've got that space, 8. And then we've got the probability x equals x. So perhaps I can trim off just a little bit of the table there. Okay, so the probability density function was given as kx over 8. So we get, for the first one, 2x over 8. And I'm just going to put 2x over 8, which is x over 4. Sorry, it shouldn't be x, should it? It should be k. Sorry, I'm not concentrating there again. So let's do 2k over 8, which gives us k over 4. We then get 4k over 8, which is k over 2. We then get 6k over 8, which is 3k over 4. And then finally 8k over 8, which gives us k. So there's our probability distribution in terms of k. What we want to do though is we want to find out what k is. So we know that the summation of the probabilities is equal to 1. So that means we know k over 4 plus k over 2 plus 3k over 4 plus k is equal to 1. Now when we simplify this, what we get is that 5 over 2k is equal to 1. And so if we times by 2 and divide by 5, we get that k equals 2/5, which when substituted into this would give a probability of 1/10. It would then give a probability of 2/10. This would then be a probability of 3/10. And the final one would then be probability of 4/10. Now the reason I've done this in terms of tenths is because the first one simplified to get a tenth, and quite often because we have to find probabilities involving these, we're going to want to add and subtract these fractions. Then you can do it quicker without a calculator if they're all the same denominator. But there's nothing wrong. I mean, I could write this as 1/5. 3/10 is fine. Obviously, this one here is 2/5. Okay, it's just a personal preference of mine. Now, actually, this question doesn't ask me to calculate any probabilities as such, but what it does do is it says if find the probability that the two successive values are equal. So what we want to do is find a probability that x1 equals x2. So what we need to do is find a probability that x1 equals x2 equals 2. And this is just a slightly different way of writing things. It's still the intersect. It's just a little bit quicker and neater way of writing it. Equals x2 equals 4 plus probability x1 equals x2 equals 6, and finally plus the probability x1 equals x2 equals 8. So calculating these probabilities, we get 1/10. Probability of it being equal to 2 is 1/10, and we multiply it by itself, so squared, plus the probability of it being equal to 4, which is, and I'm going to work with the tenths because it is a little bit easier, 2/10 squared, because it's multiplied by itself, plus the probability of it being equal to 6, which is 3/10, and that's multiplied by itself, so that's squared, plus the probability of it being equal to 8, which again is 4/10, and again multiplied by itself, so it's squared. So what we end up with is all over 100. 1 plus 4 plus 9 is 14. We get 30 over 100, which you can write as 0.3 or 3/10, however you like to write it. Okay, I hope that solution all made sense, and I hope the rest of the video has made sense and that you understand the idea of discrete random variables and how they are distributed. So finally, just to finish off, at this point you need to have a go at the discrete random variables exercise. Practice the different exercises, get used to writing out the distributions, get used to finding k's, finding probabilities, using independent observations, etc. Build up your confidence, and then once you feel confident with that topic, have a go at the discrete random variables assessment. Okay, I hope you found that all useful and easy to understand.